Yeah, thank you for coming anyway. And I want to thank Krishna though for the idea that we need to know a little bit about algebraic geometry before we move back to the multi-bit homology. So actually, I was signed. Let me tell you my assignment, right? So I was signed to talk about the language of skin in the next two talks, which is 120 minutes. And my job is to cover the chapter 1, chapter 2 of Harshon. I realized that no way I can cover these two chapters in 120 minutes. And there's another one coming after me who will finish the rest of Harshon in another two lectures. So I have no complaint. But I think I will change my plan a little bit. So instead of explain to you what is algebraic geometry 120 minutes, I'm going to explain why you cannot explain algebraic geometry 120 minutes. I'm trying to reach the opposite goal. I probably think it's easy to reach. So I'm going to not following the lecture notes a little bit. I'm trying to catch the ideas that why algebraic is formed and how the current status is. So you will see that how to get involved through the history. So in my understanding, algebraic geometry is a tool trying to unveil the curtain between two worlds. One world is what I was supposed to be working on, called the theory of algebras or rings. And presumably, they are all commutative, but you'll see that some of my works are trying to do it in non-commutative version. So I'm not going to add that first. The other world is, they are even longer than, or probably at least same, is called geometry. So what algebraic geometry do is trying to connect these two worlds or officially erase the curtain between. But there are so many ways to erase the curtain, and there are some popular ones which outsmart to the previous ones. So I'll talk all of them, and I will explain mainly why Grossetti got the award that he invented abstract algebraic geometry, or why the language scheme is a little bit better than any other approaches. So let's put the curtain still there. So I'm going to start with the left side. What is an algebra and what topics involved? So the main, I'm going to not talk history. So I'm going to start with year 1990s. And in 1990s, a person everybody knows, Hilbert, published 3 papers. In each paper, it proved a gigantic breakthrough result in algebras, and I should say commutative algebras. They are called Hilbert's basis theorem, Hilbert's now standards, and the last one called Hilbert CZG theorem. And with help of these two theorems, actually, a link is already built in between geometries and commutative algebras. And that part we call so-called classical AG. Everything before Grossetti went in. Then commutative algebra gets popped up by different area tools, right? So I'm going to talk about 3 main tools which developed through the 20th centuries until now. First is you just talk about the representations. So in order to study a commutative ring, nowadays we call the representations or modules. We study the modules over them, right? So that's one big topic in algebras or commutative algebra is talk about representation theories. And this has a very nice reflection in algebraic geometry side we learn called quasi-coherent sheaves. So that's the algebraic geometry analog for representation theory. So let me put there. And people told me, I don't know if it's a joke or not, when you see the word quasi, just means that people messed up with some definitions before, so you have to add quasi later to rescue the plan. So, which means that people have made coherent sheaf first, but they figure out they have to throw quasi to make a little difference. So we'll give a definition of both of them later. What are these? But the one thing you can keep in your mind, they're representations of algebraic geometry or varieties in the sense of representations of algebras. The other very main topic which people use to learn algebras is through the idea from algebraic topology, and they have a very solid name called homological algebra. So homological algebra becomes into being by learning some stuff from algebraic topology, and that's very linked to what we are learning now. And this is a very powerful tool. It's not only used for commutative rings, it actually works for any representations. So, and this builds into the work of algebraic geometry, mainly by Serre and his co-authors, is introduced so-called sheaf cohomology. And that's a big reason people want to learn sheaf cohomology once we learn what sheaves are, because they are probably the natural data to explain the structures of a manifold or geometrical stuff. So sheaf cohomology is a powerful thing. People trying to learn varieties or algebraic geometry based on the same idea of how homological algebra play roles in algebras. The next approach, probably the most universal approach, which Grothendieck bring into the subject, is so-called categorical theory. So instead of looking at things one by one, set by set, elements by elements, we want to package everything together in the universal framework called categories. And this has a very nice analog in algebraic geometry, and you'll see that later, especially between classical AG and we call it abstract AG, is how people view categories into these subjects. So it's happening in 1960s, where Grothendieck first time introduced the notion called scheme. I think it's in some ICN talks in Paris. I'm not sure, but he wrote a book. I mean, the first publication probably in 1960 on elements. So in here, you're going to learn everything from the categorical point of view. Functors, right? Representable functors, everything. So it's a very powerful language to bring into. Okay, so that's how the things involved between algebra and geometry. And nowadays, more and more things are getting involved, like people studying multi-vehicle cohomology, but all these things are based on these three approaches which I'm talking about. You will see their origins, and maybe now they're developing a different level, but these are three basic bricks for how you develop or study abstract algebra geometry. Okay, any questions? So let's do one by one, right? These are so many words, and we're going to learn in two topics, which I don't think we can do, but I'm trying to do as much as I can. So I'm first go from this side. Sorry, I should something which is lighter. So I'm going to do from this box first, okay, and see how this Hilbert the three famous theorems to give birth to the classical geometry. And I will talk about some issues why people want to enlarge this classical theory of AG to abstract AG to work more general setups. That's where Grothendieck introduced the schemes. Okay, so that's the approach. Then I'll talk about the three steps, how people do it. And probably won't finish today. So on Friday, we'll continue, see how much we can finish today. So that's the first thing. Let's go to the next one. Okay, so let's view the now standardize into a dictionary, right? So The dictionary is in the algebra side. You have a very nice kind of algebras. Now, I will give technical names, but if you don't know, let me know. I assume you know all the meanings, but I'm going to verbally say what are they. So first, the family of algebras we are interested in algebraic geometry are called finite generated domains. Domain just has no zero divisor. A b equals 0, one of A or B has to be 0. And it's work over base field, which is algebraic closed field. Now, doing algebraic geometry over non-algebraic closed field will be so different from doing things over algebraic closed field. So in the classical AG, usually we all work over algebraic closed field. Now, characteristic does not matter too much, even though in number theorem, maybe positive characteristic are more favored, but algebraic closed is the key. So that's very important. So I want to say in classical AG, algebraic close is the key to get everything work out. Okay, and in the other side is the classical AG object we called varieties, and for finite general domains we call affine varieties. So what are they? I'm going to explain what are they. They're just a set of points in affine space. So affine space is just a vector space of dimension n, but we don't talk about its vector space structure, but if you want to understand, it's just a vector space of dimension n. So every point has n coordinates. Now, an affine variety is just an irreducible closed set in AN. So it's just a closed set, which I talk about topology. You will see what topology are, but I'm just throw the words first, irreducible closed subsets. Okay, so the bridge between them is using now standards as one-to-one correspondence. I'm going to explain everything now for the one-to-one correspondence. So if you have a commutative domain, say R, finite generated, how are you going to get a variety? The way is to present it as a quotient of polynomial rings. How can you do that? Because the finite generated means I can pick generators 1 to n, and it must be a quotient of that by the second isomorphism theory. So I'm going to have an ideal, which we call the relations. And how I'm going to get a variety is I'm going to take so-called zero of locus. Is first by the Hilbert basis theory, because the polynomial ring is Noetherian of every ideal is finite generated. So you are able to pick a generators from F1 to Fr, which generate the ideal. So the subvariety I get on the right side is taking the common roots of these polynomials. I'm picking points in AN, which are the common solution for these generators. Now, there's some issues you have to verify. Is first, the variety I get is isomorphic. Doesn't matter how presentation I get. So I may get a different presentation, even use different number of variables. The relation will change, but the object I get on the right side are canonically isomorphic, which I don't talk about that yet. But I want to throw this in so you see that no ambiguities by picking the presentation. Second one is that this generator also does not matter. As long as you find the generators of the ideal, the set P is already determined. So it doesn't matter which generators I pick, it always give you the same set. So the map from the left side to the right side is well defined. And that's called the zero locus and finite generated domains. From the other side, it's kind of like easy to do it. So it's called coordinate rings. So what you do is, suppose I get you an affine variety, say X, is an closed irreducible set in AN. So it's not only a set, but up to some topology is closed and irreducible. So what I do is I'm going to form a quotient algebra. I take the ordinary polynomial rings in n variables, and I'm going to quotient out the so-called vanishing ideal. So what vanishing ideal means, I'm taking all the polynomials in the polynomial ring, which is identically 0 on the entire set X. And it's very easy to check, is an ideal. Close on the addition, close on the multiplication, so you can form this quotient ring. And this is called the coordinate ring of X. And the condition I put there, irreducible close, you can understand in the algebraic way, which probably easy for you to remember, is the coordinate ring get is a domain. So actually irreducible just means it's a domain. So that's how the relation between finite general domains and affine varieties get. And then we use the key idea of Hilbert basis theorem, because you only need to check finite many polynomials. And also upon this bijection, there's also a more specific bijection between points in AN, which is every point is given by its x coordinate. Also using under the same bijection, here is 0 of locus. And the other, I'm going to use vanishing ideal, because if you take the coordinate ring, it's isomorphic to K. So vanishing ideal is. And what points corresponding to is exactly maximum in K. And this special case, which we can recover points by looking at the maximum ideals, this is actually Hilbert's now standard. So you see, Hilbert's result, at least two of them. One is Hilbert basis theorem. The other now standards exactly tell you can do affine variety just by looking at these finite general domains. So one side is algebra purely, the other side is the classical objects in classical AG. And these two theorems say that you can do it, right? You may be wondering what the third theorem does. It's actually linked to the property of homological algebras. I may be able to talk a little bit about it, but that's the third theorem will relate to studying actually the sheaf cohomologies of project varieties. So that's the third theorem talk about in case we don't have time to cover it. Okay, so now we're going to talk about what happens on the abstract AG side, right? I'm trying to group everything together, so I'm not going linearly, that's for sure. Exponentially, I don't know, but definitely not going linearly on the knowledge. So now we have a sense of what classical AG is just by studying finite general domains. Now you may ask the question, why we need abstract AG? Why group-centric matters, right? So before group-centric scheme was introduced, there are a lot of other works already there trying to generalize the classical AG picture. I can mention some of them. Maybe you don't know. One is Andrew Vail, I think, French guy. So in his paper, actually very classical books called Abstract Algebra or Foundations in Algebraic Geometry, he introduced the idea called abstract algebraic variety. Let's say algebraic variety, right? Affine variety. Varieties, maybe not affine. I think it's not affine. Where he already have the idea how you're going to have different affine varieties, group them together, but he didn't call schemes at that time, and he didn't talk about at the level of group-centric introduce them. But this is like the idea which precedes the group-centric introduce the language of schemes. And also there's a lot of people do Chevrolet, who also introduced a lot of things as discrete valuation rings, which were heard in the affine scheme, the discrete valuation rings. He also did a lot of generalize these varieties into a different level, but he's probably using commutative algebra instead. So a lot of work trying to do. And now we have to focus why group-centric succeed, right? So let me also give you the picture. So in many cases, classical AG only talk about varieties, which have infinite points, and you have to work over base field K, right? So let's see, you are working with finite generated domains. Now they're good things, right? There are a lot of things we want to study for finite generated domains, but it's not good enough. Why? Because in many cases, that the things we are interested are not finite generated over field. For example, algebraic number theory, right? How are we going to introduce a framework which does not only work for curves, varieties, but also work for algebraic numbers, right? So that's something, and also other things people interested, like infinitesimal, right? These things people want to do. So why not have some theory which you can cover every commutative ring you have, and you have all sorts of notions we can work, right? That's the best thing you can do. Now, there's another level which people are trying to do these days is people want to erase this. How about give a general setting which you can do ring just by doing so-called non-commutative algebra geometry, and that's far away from completion. So that's I know that right now there's no satisfied theory which you can job commutative ring in a very satisfactory way. So that's something I don't know, but for commutative ring, it's sort of done. The best solution you have is presented, right, by Grusenty. So let's look at this algebra side. Let's look at the geometrical side. So we know that by the now standard nuts that finite general domains are affine varieties. Now, in order to generalize from finite general domains to commutative rings, we have to enlarge the things of affine variety, right? Algebraic did it for abstract varieties, but we want to do for every commutative ring, not even over field, right? Like Z, Gauss integers, and all sorts of things, right? Somebody say infinitesimals, which is not a domain, all these things. We have to do everything including that. And the most satisfied solution given by Grothendieck is to talk about the things called affine scheme. And he did not only so, he gave you what is affine scheme. Actually, he adopted the language of category theories. And that's another main contribution of Grothendieck, is he not viewing these as sets, he viewing these like categorized to make it as categories. So I'm going to give the category of commutative rings. I'm going to use double parentheses to mean a category. Now we are talking about category every time, so probably I don't need to review what category, but the extra thing we get is we can talk about the morphism between different objects, right? Previously we talked about the commutative rings, there only one ring, which you study at one time. When you finish your work, move to another ring, but you never tell me how you're going to move to it. Now everything like packaged together with this fancy double parenthesis called category of commutative rings. They not only consist all the commutative rings people dream of, but also connects all the dots between them, which is called morphisms. And that's the best thing about categories, do everything together by putting everything in the package you study. That's what I understand why category theory play more and more tools nowadays. So and this picture generalized to the category level called category of affine schemes. And the previous way, which Hilbert is so famous of, Hilbert's approach, right? He says there's a 1-to-1 correspondence. And that's the best thing we get. And it's a 19th century language. now everyone here, I don't know how many of you there, we are 21st century mathematicians. Somebody want to be 22nd century. I'm not able to be that, but hopefully one of them will be 22nd century mathematicians. But in the 21st century, 1-to-1 is not good enough. Because as Guru Sendik said, everything should be natural and take it a categorical point of view. So now the 1-to-1 also get updates. To a what? You can guess it out, right? What 1-to-1 correspondence in the framework of categories, right? It's just equivalence, right? So now we get a categorical equivalence. And the interesting thing that you have op, which means that the arrow revises, it's opposite category. Means if you have a morphism between two commutative rings, the affine scheme corresponding them, the morphism gets reversed. And that's very natural. We see some example. This should be opposite notion over there. But you see that that's all the Grothendieck did in 1960s. Right? It's the main idea. He did much more, but that's a general idea which underlined all his works, is to generalize the picture of David Hilbert's, which you state in the way of 1-to-1 correspondence between two different sets into an equivalence of category level, which everything embeds into the categorical level. But he not only do that, because we still have something we can do more, because in the big picture, we are not only talk about affine varieties. Actually, we have a different flavor called the projective varieties. I'm going to introduce them and enlarge the picture even further. Let's go to the project side. So while we talk about project variety, first time it seemed like unnecessary, right? Affine variety is good enough and it concludes all the range we need. But there are many cases you will see that projective variety is much better than affine variety. Now let me introduce the algebraic notion of project variety. What do you mean by you are doing a project variety other than affine? Is instead about commutative rings, you have an extra structure capturing the word of projectivity. What's a word capturing projectivity? Is so-called grading. And that thing I'm learning when I was starting to understand what the project is projectivity to affine varieties seem like graded commutative rings to arbitrary commutative rings. So have a grading is ensure that you're talking about projectivity, at least in the algebraic variety side. And in the other side, we have projective spaces of varieties called Pn. So, and you have a similar picture, which we call graded versions of David Hilbert, which the right side you have project varieties in Pn, left side you have finite general graded domain. Graded domain. So everything works out. People, you just need to change the three theorems in its graded version, which is people always say easy to do, but I never do it. So I don't know if it's easy or not, but you can have the graded versions of Hilbert's three theories, and you're going to get the 1-to-1 correspondence, at least from David Hilbert's result, the project varieties corresponding to the finite general grade domains. Now, I still need to explain to you why projectivity, projective space is better than affine variety. Now, you can understand projective variety in three different ways. And the three ways give in different favors. And I'm going to pick one of them as a generalization to the scheme language level. So first is you can view Pn as like sort of quotient space. So what is it? Is you take the n+1 affine space, delete the origin, which corresponding to the origin of the vector space, and put an equivalent relation on the complement. Is you say 2 points, which I label from x0 to xn, starting with 0 because they are n+1 coordinates, is same as y0 to yn if they differ from a constant scalar. non-zero scale. It's a scale. And the project space is basically the quotient space of this. That's first interpretation. Not very intuitive, but it's very elementary to remember, right? If you know a little bit C theory, you probably understand what I'm talking about. And there's the upgraded version for that, which a little bit fancy. Is just a first example of a Grassmannian variety. And this is kind of like Hilbert moduli space, which parameterize the one-dimensional moduli space, parameterize the one-dimensional subspace of n plus dimensional subspace of all of A1, A, n plus 1 dimensional vectors. So that's the interpretation number one, either the quotient space or the moduli space of one-dimensional all the subspaces of a n plus 1 dimensional vector space. Usually we call the Grassmannian 1 n plus 1. And for generalization, it can be R spaces. Okay, here R is equal to. So that's explain number one. It's a moduli space. And the moduli space parameterize all the n one-dimensional subspace of n plus 1 dimensional vector space. Now, there's interpretation number two, a little bit better, is in algebraic geometry, even though we have the same set, but the topology always weird. So I didn't talk about topology yet, but you can think about the topology as making the associative ring has a very nice property. Like the topology I put in the affine space is making all these affine varieties into domains. Okay? Or you can say the closed set are given by affine varieties, or the union, finite union of affine spaces. Right? And same thing, we can put a same thing in the project varieties, even though it's hard to explain, so I'm not postpone as much as possible. But I want to remind you that when you talk algebraic geometry, the sets are same, but the topology is different, or I can say much coarser. It's not even a T1 space. So it's not a hot-stop space, so it's different. And the topology has its name called the Zariski topology. So what's the other way to understand PN is forget about the Zariski topology. Think about the Euclidean topology, right? We have to switch our mind. Think about Euclidean space of an plus 1, an. Okay? Now, in the Euclidean space, an is not compact. It's a hot-stop space, but not compact, right? Because checking Euclidean space compact, you only need to show every sequence has a limit. Now you have a sequence goes to infinity, so it never compact. So what is Pn? You can consider as a one-point, compactification of An. But you have to say under Euclidean topology. As a set is same. So let's give some reason why Pn is better than An. Because if you go back to the usual topology, Pn is compact. And we know compact hot-stop space is more like a manifold. So many things which true for manifold, or many words we can use for manifold works for Pn, but it may not work for An. That's why the reason Pn is better than An, right? And then that's a third way, which is the way Grothendieck used to define varieties, is to consider Pn in a way is like a manifold. Everybody know manifold. I don't know manifold too much, but at least know the definition. Is you group things together, right? Or locally speaking, it's trivial. So if you have manifold, it's locally like a Euclidean space. Then you patch these Euclidean space. So in order to describe a manifold, you have to have the local patchment and also transaction functions. And that's how you understand the math transaction. How you putting these local patch together, patchment. Okay, now we can view Pn as a local patchment of affine spaces, and that's the way to view Pn. At least in algebraic geometry, that's the most common way. Is I can view it as a n+1 attachment. I don't know if the right word. If not, please let me know. Affine spaces. An. Now I have to be a little bit precise. What these affine space? Actually, there are n+1 of them, and what are the transact functions? So let me explain a little bit. So in the Pn, by the first description, it has a so-called homogeneous coordinate. That's called homogeneous coordinate. And it's not unique, always up to a scalar. But this is called homogeneous coordinate of a space. So you can pick a point and take its homogeneous coordinate. And the way you delete the zero means that if you look at all the coordinates, they cannot be all zero, correct? So there must be some coordinate non-zero, sum of, right? So the ith piece Pn is exactly the collection of points, set of points where the ith coordinate non-zero. And for example, the first patchment is the first coordinate non-zero, second is x1, the last n+1 is xn. Since some of them has not be zero, so you know all the union of all these affines is a set of Pn. And you can further show that if, for example, the first piece of An, which is basically x0, non-zero, all the others, you can be anything you like, then you can rescale it, which by the equivalent relation, you always can do it. The first into one. Now, when you fix the first coordinate, all the others cannot rescale again because they only can differ from a common scalar. If the first one fixed, then there's no way you can differ from the remaining one because you cannot scale them all. So this will give you one-to-one correspondence to An. So that's why you show that the Pn is the patchment of n+1 affine spaces by letting some coordinate in the n+1 equals exactly 1. Okay? Now, why need to spend so much time to talk about the project space? Because this gives us an idea how we're going to do for affine schemes, two schemes, right? So let's go back to the picture. So now we do the algebra side. We have David Hilbert level set bijection to the category level. But you see there's another space which we can add to it if we can is if you look at the affine varieties, there's something which involving all the affine varieties, we call the project varieties, and we have a name which called quasi-project variety. Basically can means that there's affine variety plus project variety because affine varieties are not project varieties. But you can consider affine variety as open sets of project, and these open sets are called quasi-project varieties. And as I said before, once you see a quasi, it means somebody mixed up with the definition before, so it should not be there if we build define project variety correctly. But that's how we have now. So you can enlarge the category of affine varieties to at least quasi project varieties. which involving all the project variety and the open set. So that suggests that there should be a similar picture people can do in this level by enlarge affine schemes to a bigger category, which just like you do for quasi-varieties. And the way you do that is you take 1, 2, 3. 1 is hard to do it because there's no quotient space you can get from a variety. Set 1 also impossible because you have to use Euclidean topologies. And many schemes are not even have a field. So the only way which you can do it to enlarge this affine variety is to follow the third one. And that's exactly you're going to get the scheme category. Okay, I can write here. So now you have a bigger one, which the right side I don't have, but you can enlarge this into a big category, and this is called fourth subcategory. And this is what you get the category of schemes. Okay, so, and I can even give you a definition, even though it doesn't make sense right now, but I'm going to try to make it sense in probably in the remaining time is now we have the definition, right? What is the category of schemes? Now, following the Grothendieck approach, we are not allowed to talk about things alone. We have to talk about the category involving the things. That's the right attitude, right? So what is the category? Now, the object is exactly the schemes and patched by affine scheme. So we can say it's a, actually we have to use the word I'm going to explain, but let me a little bit technical, locally ringed space, which locally isomorphic to some affine scheme. Okay, so you can explain, I will explain this soon, but let me postpone it. But the best way to understand is you have a topological space, which you have some open bases, which on each open base is just the same as a affine right given by spec A, right? We don't know spec yet, but the functor, which I should explain here is a spec. That's actually a functor, which make this equivalence. So spec locally is like spec A for some commutative ring. Now we also need to talk about morphisms, and that's something we have to do if we are doing categories. So that's when you talk morphism, that's why the word makes sense, because we never know what the morphisms are. We sort of understand the morphism between affine because it's just corresponding to the morphisms between commutative rings, and we know what the ring map is. But when you enlarge it, it's kind of hard to define because we don't know if you are out of the ring what kind of morphism is. So that's why you have to be a little bit technical, and that's called local ring space. So it's morphism of local ring space. So you can understand this as by, I want to study local ring space because that's good notion of morphisms inside. If I only talk the affine schemes grouping together, probably it's hard to talk about what our morphisms are because you have to respect these transaction functions. And we are not in analytic topology, so what transaction function you can have. But once you do the local ring space, things become throw into the rug once we have this notion. So it's not something we have to do it, but just make things a little bit better. So that's my understanding. It's not the essential idea. The essential idea is what you look at PN, building up of PN. Okay, so now we have to do a little bit more general. So we know that the category of commutative rings is equivalent, maybe I use up here, the functor is spec to the category of affine schemes, and that is equivalence. And we enlarge this one into larger category called category schemes. And now, and actually it's not stop. Don't think Grothendieck complete everything. Now we're just sitting and enjoying and eating. We still need to producing it because it's not complete story. So nowadays people trying to do more general stuff. So build up affine scheme, there are more bigger spaces. As I know, at least there are two of them. There are more nowadays, but I don't know too much. So I only have to tell you what I know. Is you can go to the idea of stacks. So first thing you can do is can enlarge it to algebraic spaces. And algebraic space is become the notion of stacks. The only two stacks I know is delay Mumford and Artin stacks. I don't know all of them because I heard they are notoriously hard to understand. So that's all I have right now. But you see, from the general idea of communal rings enlarged to affine schemes, now we have enlarged to schemes that have more general space categories called algebraic space and even stacks. That's one direction people do. Probably we'll see a lot in the motivated homology. And each step, when you enlarge it, because you want to make something better. And that's the reason you want to look at larger and larger categories. So one thing I can say, the reason people want to get, which I said, the modularized spaces. And that's one of the reason people want to study larger category than scheme, because many things we get are parameterized space of geometrical space. Like the things we already see is the Pn. That's the modularized space if Grassmannia P1, right? So Pn parameterize all the one-dimensional spaces of n plus one-dimensional space. And we are lucky it's a scheme. It's not a scheme, it's a classical project variety. But in general, if you want to parameterize geometrical space, like all the curves, right? All the varieties of dimension n, that's not true that the modularized space can have a natural structure of scheme. Now you are lucky, but most time it's not. So how are you going to make things work? It is you have to look at larger categories, which by the unit property, the representable the functor which represents something to the set is representable, not by a scheme, but by a stack. So that's one of the reasons people want to look at stacks, is because many modularized space don't have nice representable objects in this category of schemes. And there's another way, which we already use it, is using so-called locally ring space. And the category scheme, the special case of locally ring space, actually, the locally space which locally given by affine scheme. If you're not locally given by affine scheme, it's still a locally ring space, but it's not a scheme. So you can think it as a larger category of schemes. And beyond that, there's another notion called a topos. That's a different direction people study of schemes. And that's only two notions I know. Probably know more, but that's all I can tell is how people evolve from looking at commuter rings. Oh my gosh, now you have such things crazy like this. Okay. So what do we do, right? How many things I learned? Okay, so now I have to be a little bit theoretic. Is let's look at the big picture, how much I have covered, right? I do the three things, give you the greater version. I talk about this. Now we have to go this approach. I talk mainly on the categorical approach, right? You see, the category theory reflects in AG is moving you from classical AG, which you look at individual objects with individual properties, enlarging to look at the categories and the functors between them, right? You have commuter ring category, opposite affine scheme category, topos, stacks. Now, there are two more things we have to talk about, and I'm going to talk about their incarnations, especially in classical AG, maybe not abstract AG, is how you're going to do representations, how you're going to do homological algebras. All of those things bring into the main idea of sheaves. So sheaf is a very powerful thing. Actually, if you learn manifolds, it probably exists much earlier than algebraic varieties or schemes. So what they did is Sarah introduced this notation into AG and developed the whole thing called the sheaf cohomologies. And one actually main motivation of developing sheaf cohomology is to solve the well conjecture. Is at that time well conjecture. If you look at these trace functions of the all the what kind of functions, maybe it's modular functions at variety counting points, you should get a rational function. And the only way there, which using the idea from manifold, you look at the Lefschetz fixed formula, and you have to need to have certain cohomology to do it. So all the motivation behind the Grothendieck introduces and scheme, they're trying to get a well cohomology, we say. And so well cohomology is conjecture well cohomology, and also later develop étale cohomology. And that you can do sheaf cohomologies to mimic the way people did for Lefschetz fixing theory manifold. After that, you can prove well conjecture, and it proved in 1970s. So that's the main idea. Actually, people introduced it. That's very powerful. So for the remaining time, I'm trying to give a quick introduction to sheaves, and maybe next lecture, I'll talk about more detail how to get representation theories and how homological algebra works when you work with sheaves. So what is a sheaf, right? So we forget about the ring space. Actually, all the things can be done by understand sheaves on algebraic variety. But let's do a more general setting. Yes, I'm going to talk about a topological space. I'm going to build a category out of it, just like I'm building a modules category over ring, right? So I'm going to build this to a sheaf category of X. And this mimic in the algebra side is you have a ring. So topological space is the main objects in the category topology, just like ring is the objects of the category of rings, right? You can build a representations called model. Now, there are similarity between these things because these are all so-called abelian categories, which means you can do cohomology series by looking at derived functor if you have enough projective injective objects. But the very nature is sort of quite different. You will see that this category is much harder to learn than the model category, even though affine scheme, they're equivalent. But in projective varieties or general schemes, the sheaf of cohomology is much subtle to handle than the module category. But the idea is the same. You want to study representation category. So what is a scheme? There are two ways to define a scheme. One is topological way, easy to understand, but probably hard to compute. The other is functorial way. So let me talk about the topological way to define a scheme. So not scheme, a sheaf. So topological way of defining a sheaf. So if you have a topological space, a sheaf on X, it can consider as a étale space. étale space. E over X is a surjection. And what is étale space, right? Just a continuous projection to X where it's locally homeomorphic. So it's in continuous map from X, which is a locally homeomorphic, homeomorphic. And having a étale space of X is, you will see that is same as having a sheaf on X. So that is a topological way to define sheaf. And the other way, which is equivalent, is I'm going to see it as a functor. And that is way Grothendieck appreciate because it's easy to generalize. This way is topological, easy to understand, but it's hard to generalize to a very abstract way like Grothendieck topology. Then you don't know what étale space is. But if you do the functorial way, it's easy to generalize. But sometimes it loses its intuition. So I want to say it's pro and cons. That means that the categorical approach is every time is better. Sometimes not better because it's sometimes losing some intuition, which we really need from the topological side. So I can how to do that? Let me do a down-to-earth definition, and I'm going to say it's just a categorical way to do it. So a sheaf on a vector space X is actually an assignment, which it gave me an open set in X, I'm giving you a set. Now, usually Shiv, you can see Shiva sets, Shiva abelian groups. It just means the target is. So I'm going to say Shiva sets, but in algebraic topology, probably everything is abelian groups. So I'm going to be a little bit precise. It gave an abelian group. So every open set, you're going to assign an abelian group. So F is like a map. Input is open sets, output is abelian groups. But you cannot assign every arbitrary abelian group to open sets. You have to be a little bit delicate, which means that you need functorial properties. So if you have inclusion from one open set to the other one, open inclusion, then you're going to have a restriction function, which backward. So you have open set from U, open set on V, which you have a restriction map, which I'm using rho UV. Sometimes people use other notations. I'm going to use rho UV. And since abelian group, I can take element-wise. So elements in SU called sections on U. And the restriction to sections on V, usually we use S/P, just means which is equal to rho UV R set. Now, this restriction cannot be anything. It has the functorial property, which means that if you do rho UU, you have identity. And if you do two restriction, one after the other, the same as you do restriction once for. And actually, you see, actually, this is not enough for sheaf. That is actually, we have to be precise. This is called a pre-sheaf. If you have this property, functorial, and a sheaf, F on X is a pre-sheaf which satisfies the sheaf property. So what is the sheaf property? I'm finishing soon. So if you can bear with me, hopefully you can bear with me a few minutes. I'm almost finishing. So sheaf property is topology means that the data is locally restorable. Means everything which you know about sheaf is hidden in the local data. So if you know properties on open basis, you should know sheaf on every open set. So that's the magical of sheaf. So which can be more precise is if you give me sections on any open cover UI of an open set, you satisfy the compatible condition. Compatible condition, which means that if you have sections in UI, UJ, SI, SJ, if you restrict to their intersections, they're always same. So UI, UJ, same as SJ. Then there is a unique grouping. You can group into one single section. So that is a unique, very important section S in U such that S risk UI is the local data. Okay. So this is a sheaf. Looks very horrible to understand, but conceptually it's easy to generalize, even though this definition is much better to understand, but you see how to generalize. So they're pro and con. That's why I want to throw them together. They're equivalent. So the last thing I'm going to do, I'm going to show it's equivalent. And the equivalent is pretty easy to do. It's not that terribly hard. So I'm going to show that etal space over X is actually the same as having sheaves. So I'm going to use this topological space X to abelian groups. All right, I should have said, but I'm going to like sheaf functors satisfies sheaf property. So one thing I should say is that the first condition for being a pre-sheaf can be reinterpreted as a functor from space of topological spaces to abelian group, probably contravariant functors. And the topological space is a category which objects are open sets and the morphisms are inclusions. So you only have open sets as objects, and the morphism between these open sets, if one is included in the other, you have a morphism. Only one morphism. If not inclusion, they overlap, you don't have anything between them. And this idea, you will immediately see why it's easy to generalize is because you can replace by any category you want, as long as you have the idea of how you take open intersections or unions. So that's where Grossendi introduced the idea of Grossendi category. So that's you see why this category is easy to generalize. Open. And you need add the sheaf property to make sure it's not a pre-sheaf but a sheaf. Now let's talk about this at the last few minutes. So suppose I have a etal cover. How are you going to get a sheaf? Actually, it's very easy. You just do the called sheaf of sections. So if you give me open set, what are the abelian group you get? I mean, you're going to take all the sections from X to E, which you compose them. So you go to I. Actually, you're going to restrict to sections on U. You compose with projection, you get identity on. So if you give an etal space, the sheaf of sections on an open set U, you just take all the sections from U to E, which you compose the project, you get identity. And the backward, if you get a sheaf on X, how am I going to recover the etal space? That's also easy. So you need a notion of stocks. You just add the union of all the stocks. And you put a topology here to making sure that the natural projection, which maps every stocks or the fibers to X, become continuous. The call this topology making this projection continuous. And there's a way to check, which is I'm not going to do it, is that's a one-to-one correspondence. So if you have etal space, you're going to get a sheaf of sections. If you have a sheaf, you can recover this etal space by taking the union of all the stocks, the locally Jim functions. So let me be a little bit precise if you don't see the notation before. So it's taking all the sections, but taking the limit. So you take all the possible sections around X for some open set, and this means that you identify two functions if they agree on some smaller open set. And it's a good way to see that this etal space description is same as this. And you just check directly. I'm not going to do it, but it's very easy to show that. And one thing before I finish is the interesting thing about this etal description is that even though it's locally homomorphic, but this space is generally not hostile. So it's not something you can think about as vector bundle, which we'll talk about next time. It's usually not hostile. It's a very weird space. So etal space is not something which you can do by using the way of manifold. It's very strange. So even though you have a covering space, the space is not very well defined. It's usually not hostile. Okay, everyone, I think I should stop now, and I'll probably continue next time. By the way, do you have any questions?
Yeah, let's stop our recording. Thank you so much, Dr. Wang, for this wonderful talk. And yeah, we'll see you in the next one.
Cool. See you guys.